Yeah, okay, we continue from the other video where we did equation-oriented modeling and do the process simulation on it. And then we now in the second mode of equation-oriented in Aspen PLUS, which is we have to do the optimization. So the same process still, and then I just simply add or take out the reboiler duty and then the condenser duty out of the simulation, basically. So if it says so it's if we sequential modeler, we run it as our initial. Yeah, just to let you know. Take some time. It's still the same spec here, by the way. Yeah, the results are there, and then well, let's see what the results is. In mass, so we have yeah, the same 39,000 kilogram hour of distillate rate and 4 reflux ratio. And now we because we have the duty calculated at as in like kilowatt, for example, or megawatt, to make it easy to read. So 17 megawatts in the condenser, and then 12 megawatts in the reboiler, basically. So so if we take into account all of these duties, so how we do that is simply we define yeah, in the spec groups we do the same flipping conditions, right? So we have this distillate mass and reflux ratio mass, we flip it from constant to calculate it in the EO later, and then these guys instead of being constant, we spec it and optimize. Yeah, it was constant in the previous video where we set the value to be like yeah, these numbers, right? So a very small number for the ethane in the distillate, and then somewhat small number of ethylene in the bottom stream. So this was the previous video, and now in this case we are going to optimize this. So that means these two variables, they will be running. Aspen will then find what is then the optimum values for these two in such a way that we will then maximize the profit. So how to calculate the profit? So we define the objective function over here. We find the profit, click a new, and then click on profit, and then the direction is then to maximize, and then we put scale 1, and then unit is then dollar per hour. And how we define it is that yeah, this is where we put the dollar per hour. We maximize it, and then we simply yeah, we run first to get all of these variables available, which we can then later on create from here. So we just put some names, for example, cost of condenser. So we take out the condenser heat, and then so in this case the unit, the standard unit, if we go to the variables, yeah, we don't run it yet. Then if we say, for example, yeah, just to see, so instead of optimize, we do calculate constant, and then we do constant, so that we do the simulation, so that you know, equation oriented, and then simulation. Yeah, this one we can. Okay, and click run. Yeah, we have all the variables over here, right? And then then we can see, for example, if we want to see what is the objective again, profit. Yeah, this condenser. Can you simply scroll on this condenser? Unit is in watt, and the flow. This is the physical type, and then the spec is calculated. So we can and then somehow. So it's unit of energy, right? In watt. Somehow I have the unit, the price unit as in this number. So I just put it there. The condenser is this much, and then the regular is the 10 times higher, and then the distillate mass is then this number, right? So this is how much we can get by selling the distillate, and this is how much we can get by the for the bottom, which is then this is the ethylene, this is the ethane. So we want to maximize this, right, and give it a name, and then we have to switch the spec from constant to optimize, so that then it knows to optimize. Right, as you can see, previously it was like say for example constant, these two. The 0.02 of ethylene in the bottom, the one that we put, right? Now, once we define which variables are optimized, which variables are calculated from this flip, and then we define the inputs of the objective function. So it's all in linear fashion, if you recall, in linear fashion, and then objective. Now, when we create it, it's in linear fashion, and then this is how we put the price. So it's if it's like we are getting money, we put positive, like in this case. If we are losing money, we put negative, like in this case. Yeah. So that's basically what it is. So this guy multiplied by that guy, this guy multiplied by that guy, and then this multiplied with that, this multiplied with that, and then we sum all of this as the objective function. So once we do so. Once we define it, and then in the EO inputs, because these are the ones that we're going to optimize, right? We need to find what is the optimum volume values for these two. So we just simply this is the existing number. We just simply put like a lower bound and upper bound for these two variables, and then we can then change it to optimization. Select the profits, and we run it. Yeah, so we'll see in the results. 1 second. So so the initial value is 53,000, and then the optimized value is 80,000. So that's the objective function. So we have an increase, and then we can see if we want to see the optimum variables. So this condenser duty, it was 6,000, and then it needs to be like yeah, it increases to 9,000, and the reboiler is then 43,000 goes to 73,000, in such a way that we are making more distillate, yeah, from here to there, and then less of the bottom stream, because it's a very cheap one. We put some more to the top. So that's the how the variables are changing. Let's see if we can see what the result is. Yeah. So this is then the results of the reflux ratio 5.9 with the distillate rate. So we can see that from the increase in duties, yeah, we have increase in the reflux ratio. So I think this is then the example of how to use equation oriented modeling for optimization. So see you in the other video.